In this section, the main topic will be inverses. First, I want to motivate what an inverse is by first introducing identity matrix. What is an identity matrix? What is the 2 by 2 identity matrix? Well, it's a matrix, and it has ones on the diagonal and zeros elsewhere. Since this is 2 by 2, in this section, we're only going to talk about square matrices. A matrix is square if the number of rows, the number of columns are the same. This is our 2 by 2 matrix. So we call it I2. Identity matrices are always square. I3 would be, well, you put ones on the diagonal. So it'll be a 3 by 3 matrix. You put ones on the diagonal and good old zeros elsewhere. If you wanted to talk about I4, it only has ones on the diagonal. First row, first column has a 1. Second row, second column has a 1. Third row, third column has a row. Fourth row, fourth column has a 1. Zeros elsewhere. Now, identity matrix is very similar to the number 1 in multiplication. If you take any number in the world, call it x for the moment, multiply it by 1, you get back that number x. If you take 1, you multiply it by any number, you get back that any number. The identity matrix is very similar. If you take the 2 by 2 identity matrix and you multiply it with a 2 by 2 matrix, you will get back that 2 by 2 matrix. Whether you put the identity matrix to the left of the 2, 0, 10, negative 2 matrix, or if you put it to the right of this matrix. Either way, when you multiply by the identity matrix, you will get back the same matrix that you started with. So, this asks the questions about inverses. While studying a subject called linear algebra, my teacher introduced the identity matrix, and he clearly said our models after the number 1. I realized, you have the number 7, you can multiply it by something to get 1. That something will be 7 inverse, 7 to the negative 1, which is 1 over 7. If you multiply a number, if you multiply 2/3 by its inverse, that is 3 over 2, you get 1. You get back the identity. If you're given a matrix 2, 3, 1, 4, is there anything that we can multiply it by to get back, or to get the 2 by 2 identity matrix? Now, if this matrix is called A, then this mysterious matrix, is called A inverse. The inverse of A. What do you multiply A by to get the identity matrix? Again, in this section, all our matrices are square. One technique that works all square matrices, or to find the inverse of all square matrices. But it's a bit too tedious for a 2 by 2 matrix. To find the inverse of a 2 by 2 matrix is much more mechanical, nice and quick. If you have A, B, C, D, a 2 by 2 matrix. You want the inverse. Well, the first thing you do is you interchange these two numbers. The D's up here, the A's is down there. And then you keep the numbers in the B and the C location in the same location. But you change their signs. B becomes negative B, and the C becomes negative C. And then one last thing. You multiply by a scalar. The scalar will probably be a fraction. If it's anything other than 1 or negative 1, will be a fraction. It's 1 over this product, which is AD, minus this product, which is BC. This here is the recipe to find the inverse. For example, what is the inverse of 2, 3, 1, 4? The matrix right above. What is the inverse? Well, first, or second if you prefer, you interchange these numbers and you just change the signs of those numbers. This 3 becomes negative 3, the 1 negative 1. You can do that first, or you can do this part I'm about to do first. Doesn't matter. It's 1 over this product, which is 8, minus this product, which is 3. And 8 minus 3 is 5. And there is your inverse. Right here is your inverse. If you want, you can absolutely say it's 4 over 5, negative 3 over 5, negative 1 over 5, and 2 over 5. Of course, 1/5 times 4 is 4 over 5. 1/5 times negative 3 is negative 3 over 5, etc., etc. They're a very mechanical way of finding the inverse of our 2 by 2 matrix. Now, I'm a believer that you shouldn't believe anything I say, anything your teacher says, anything your textbook says, anything your friend says, just because I tell you that this is the inverse of A. Maybe I'm wrong. Let's multiply and see if we're getting the right answer. Let's take the inverse of A, which is this, and actually multiply it by 2, 3, 1, 4. Now, you can do this scalar multiplication at the very end. That is, it's 1/5 times whatever these two matrices multiply out to. Well, when you multiply or dot the first row with the first column, you'll get a result. And that result will be 8 minus 3, or 5. And when you multiply the first row by the second column, 3, 4, I didn't mean to put a division line, you will get 12 minus 12, which of course is 0. Now you take the second row, negative 1, 2, and you dot it with the first column, 2, 1. You get negative 2 plus 2, which is 0. Second row, first column. That's where I put it. Second row, first column. Second row, second column. Negative 3 plus 8, or 8 minus 3. It's 5. 1/5 of 5 is 1. 1/5 of 0 is 0. 1/5 of 0 is still 0. And 1/5 of 5, or 1/5 times 5 is 1. And yep, we got back the identity matrix. Now, want to make one last comment, and then we'll try another 2 by 2 matrix, find the inverse of another 2 by 2, and then we'll do a couple of 3 by 3. Over here, I multiplied A inverse by A. You could multiply A by A inverse. You can take A and you can multiply it by A inverse. 1/5, 4, -3, -1, 2. I'm not going to prove this, but this number can come in front. The scalar can come in front. That is, it can be 1/5 times the product of the two matrices. And if you actually bothered to multiply this out, you will get the 2 by 2 identity matrix. Let me close the bracket that I opened over here. So finding the inverse of a 2 by 2 matrix, it just isn't that bad. It isn't bad at all. You have to know the formula. If you want to find the inverse of 2, 5, -1, -3, what's the inverse of this? Well, it's 1 over this product, which is -6, minus this product, which is -5, and that's -1. -1 times the 2 and the -3, you just switch the order, and the 5 and the -1, you switch their sign. -5, 1. This fraction happens to be -1. -3, -5, 1, 2. I wouldn't really leave a scalar of -1 that we actually multiply each and every entry by -1. And what happens when you multiply a number by -1? The sign changes. Don't spend too much time on that. You multiply numbers by -1, the sign changes. So we calculated the inverse of 2, 5, -1, 3, and minus some silly error. There is our answer. If you wanted to make sure that I'm right, you would multiply these two matrices in any order that you like. Any order that you like. And you will get 1, 0, 3 minus, you get 0, and 1. Trust me, I did that, and I did get back the identity matrix. Okay. Now, let's up the level of difficulty. As I said at the beginning, there's one technique that works for all size matrices. Unfortunately, it's not the technique that we just did. It is not the technique that we just did. If you want the inverse of a 3 by 3 matrix or larger size, in fact, the technique I'm going to use now will even work for a 2 by 2. But it's harder than the method I've already showed you. If you want the inverse of this matrix, it's this 3 by 3 matrix. You augment it with this 3 by 3 identity matrix. We'll call this matrix A, and of course this is pi 3. We are going to RREF the left matrix. And of course, whatever we do to row 1, we do to the whole row 1. Whatever we do to row 3, we do to the whole row 3. And the same for row 2. And what we want to do is get what's to the left of this line to be the identity matrix. The inverse only exists. Not every matrix has an inverse. For example, there's nothing that you can possibly multiply this by. There's absolutely nothing you can multiply this matrix by to get identity. In fact, you'll always get the zero matrix. So not every matrix has an inverse, but for right now, all our matrices are going to have an inverse. And if it's going to have an inverse, it's going to be row equivalent to the identity matrix. What is row equivalent again? It's what you get after you perform some row operations on a matrix. All right, so I have my non-zero entry right there. I want to get the one underneath it to be a 0. The last entry already is a 0, which is wonderful. So we need to do, we need to do row 2 minus row 1, which we can kind of do in our head. So we have 1, 0, 1, 100. And 1 minus 1 is 0. And 2 minus 0 is 2. And 0 minus 1 is negative 1. And 0 minus 1 is negative 1. 1 minus 0. And then 0 minus 0. In this third row, we're not doing anything to. So it stays just like it is. Okay. Now, there's my pivot number. I want to get what's above it to be 0, which it is, and I want to get what's below it to be 0. So I'm going to change row 3 using row 2. But we're going to concentrate on that second column. We want that number to be a 0 here. Well, if I double row 3, I'll have a 2 here. And if I do nothing to row 2, I'll have a 2 here. I'll just subtract. This is telling me I'm not doing anything to row 1. I'm not doing anything to row 2. Something's disturbing me. 1 minus 0 is 1. I hope I didn't say 0. It's bad enough I wrote 0. Okay. The second row is this. Let's line it up a little bit cleaner. And now I add. Well, I take that back. Now, we need to figure out the third row. 2 rows 3s are 0, 2, 2, 0, 0, 2. Multiplied each of these entries by 2. And then I write down the row above it. I write down row 2. And then I subtract because I want this to be 0. 0 minus 0, 2 minus 2, 2 minus a negative 1, 0 minus a negative 1, 0 minus 1, and 2 minus 0. So I get 0, 0, 3, 1, negative 1, 2. And now I need to deal with column number 2. So let me just erase my side work. So we just row reduce, or we RREF, and what we get in the end will be their inverse. I have this 3 here. I want to get those 1s to be 0. Well, 3 minus 3 is 0. If I triple row 1, I'll have a 3 here. If I do nothing to rows 3, I have a 3 there. I will subtract. Now, the negative 1. If I triple row 2, I will have a negative 3 here. If I do nothing to row 3, I will have a 3 here. If I add, then and only then do I get the result I want, namely 0. So let's see. Row 3 doesn't have anything next to it. It doesn't change. 1, -1, good old 2. Now row 1 is 3 times row 1 minus row 3. The new row 1 is 3 times row 1 minus row 3. 3 times this. 3 times 1, 3 times 0, 3 times 1, 3 times 1, 3 times 0, 3 times 0. And I write down row 3. 0, 0, 3, 1, -1, and 2. And I subtract because I want this to be 0. 3 minus 0, 3 minus 1, 0 minus a -1, 0 minus 2. Now, this becomes the first row. 3, 0, 0, 2, 1, -2. Now we need to do this to find a new row 2. 3 times row 2. 3 times 0, 3 times 2, 3 times -1, 3 times -1, 3 times 1, 3 times 0. And I just write down row 3 now. And I do elementary school addition. 0 plus 0, 6 plus 0, well, -3 plus 0 is not elementary school. -2, 2, and 2. Okay, and then might as well divide all of these by 2. So you get 0, 3, 0, -1, 1, 1. This matrix here is in what I call modified RREF form. It doesn't have the leading entries as 1. We divide each of those rows by 3, only because the leading entries in each row is 3. So when I divide the first row by 3, I get 1, 0, 0. 3 divided by 3 is 0. 0 is 1, 3 divided by 3 is 1. 0 divided by 3 is 0. 2 divided by 3 is just that. 1 divided by 3 is just that. And lastly, the -2 divided by 3 is just that. And now I want to divide each entry by 3 again. I'll get 0, 1, 0, -1/3, 1/3, and then 1 again, divided by 3. And now I'm going to divide each of those 6 numbers by 3 to get a 1 there. I get 0, 0, 1, 1/3, -1/3, and good old 2/3. So we now know, since this here is the identity matrix, then this here is their inverse. And the inverse, I can factor out this 1/3. Every one of those 9 numbers is being divided by 3. Dividing by 3, dividing by 3 over 1, which is 3. 3 over 1 is 3. Is the same as change division to multiplication and flip over the 1/3. Is the same as multiplying by 1/3. So our first row will be 2, 1, -2. The second row would be -1, 1, 1. Last row, 1, -1, 2. 1, negative 1, good old 2. I claim that that scalar product is the inverse of A. But who knows? Maybe I'm wrong. Okay, lots and lots and lots of room to make very silly, simple arithmetic errors. There's a finite number of arithmetic calculations you can make before you make an error. I had a very, very, very bright math instructor, quite bright, and I think he can do 3 before he made a mistake. Alright, so I'm going to take the inverse, 1/3, 2, negative 1, 1, 1, 1, negative 1, negative 2, 1, 2. That's A inverse, and I'm going to multiply it by A. 1, 0, 1, 1, 2, 0, 0, 1, 1. And like I said earlier, you can do the scalar multiplication at the end. You can multiply the 1/3 by every entry in that matrix, the first matrix, or you can multiply every entry in the second matrix by 1/3, or you can find the product of the matrices and then multiply each entry by 1/3. That is divide by 3. And when we do this, 2 times 1 is 2. 1 times 1 is 1. Add them, get 3. This product is 0, so you get 3. And when you do the 2, 1, negative 2 by the second column, when you dot that, you get 0. And then when you dot it with the third column, you get 0 again. And when you dot the second row with the first column, you actually get a 0, and then a 3, and then a 0. And the third row, when you dot it with the first column, you get a 0. The second column, you get a 0. And in the third column, you get 3 again. Actually work it out. And when you take 1/3 of each of these numbers, 1/3 of 0 is 0, and 1/3 of 3 is 1. So you do, in fact, get the identity matrix. Okay, so we did not make a mistake. Let us try one more. Next section, we'll talk about why on earth we are bothering to find inverses. Suppose we want to find the inverse of this. 1, 1, 0, this 3 by 3 matrix. 1, 2, 2, and say 0, 2, 1. I want to find the inverse of this matrix. First thing you do is you say, well, it's a square matrix, so maybe there's an inverse. And you augment it with the identity matrix. There is no inverse if, when you reduce this, you don't get the identity. That is, you get a row of zeros. All right. I have a non-zero entry in the top left corner. I want to get what's beneath to be zeros. Well, the last entry is a 0. It's the 1 that's the problem. If we do row 2 minus row 1, that is 1 minus 1, we'll get 0. So we're not doing anything to the first row. We are not doing anything to the third row. We're doing basic subtraction here for the second row. 1 minus 1, 2 minus 1, 2 minus 0, 0 minus 1, 1 minus 0, 0 minus 0. So column 1 is now done. Row 2, we go to the first non-zero entry. We want to kill off the 1 and the 2. Well, to kill off the 1, we'll just do row 1 minus row 2. Because 1 minus 1 is 0. Okay, but for row 3, it's a bit more complicated. We have a 2 here and a 1 up there. Well, if I keep row 3 the same, I have my 2 here. If I double row 1, if I double row 2, I'll have a 2 there. 2 times 1 is 2. And when you subtract 2's, you get 0. 2 minus 2 is 0. Okay, so this is going to be row equivalent to row 1 minus row 2. 1 minus 0, 1 minus 1, 0 minus 2, 0 minus 2, 1 minus a negative 1, which is 2, 0 minus 1, 0 minus 0. The second row is not changing. The third row, however, is. It's row 3, 0, 2, 1, 0, 0, 1. Take away 2 row 2's. So multiply each entry in row 2 by 2. 2 times 0, 2 times 1, 2 times 2, 2 times negative 1, 2 times 1, 2 times 0. Two times 1 is 2. I knew that was an error because I wanted to get 0 right here. 2 minus 2 is 0. 0 minus 0 is 0. 1 minus 4. This number minus that number is 2. 0 minus 2. 1 minus 0. I hate negatives. I hate a negative being here. Multiply by negative 1. So the sign changes. 3, negative 2, 2, negative 1. Okay. So now I want to clean up row 3. Here's my first non-zero entry. I want these 2's to become 0. And, like always, I'm going to use, in this case, row 3, the row that had the non-zero leading number, the first non-zero number. Okay, between 2 and 3, because I don't care about signs. 2 and 3, the least common multiple is 6. So I don't care if I get 6 and 6, or a negative 6 and 6, or 6 and negative 6, or negative 6 and negative 6. I'll figure out whether they add or subtract them to get 0 afterwards. I want this to be 6 or negative 6. That is, I will triple row 1. I will double row 3. When I triple this, I get a negative 6. When I double this 3, I get a 6. I add to get 0. Oops, this 3R1 didn't come up. So I add. If I triple row 2, this puts a 6 right here, positive 6. And if I double row 3, puts a 6 here. This time, I want to subtract to get 0. You need to be able to do that. Way too many teachers don't like students to subtract. There's absolutely nothing wrong with subtraction. Okay, so let me do my work here. So the third row is not changing. First row, 3 times row 1. 3, 0, negative 6, 6, negative 3, 0. 2 times row 3. 0, 0, 6, negative 4, 4, negative 2. And if I just happen to add these row of numbers, I get 3, 0, 0, 2, 1, negative 2. 3, 0, 0, 2, 1, negative 2. Okay. Now, let us do this little calculation. And it looks like once we do this, we'll be in what I called modified RREF form. 3 times row 2. 3 times 0, 3 times 1, 3 times 6, negative 1, 1, and 0. And I'm going to take away twice row 3. 2 times 0, 2 times 0, 2 times 3, 2 times negative 2, 2 times 2, 2 times negative 1. And when I subtract, I get these results. Okay, 0, 3, 0, 1, negative 1, 2. Okay. Now, the left matrix is almost in RREF form. Why is it not? The leading entries are not 0. Sorry, are not 1. I'm going to divide the first row by 3, the second row by 3, the third row by 3. Then I say, you know what? This is almost the inverse. When I divide each by 3, I can pull out the 3. That is, A inverse is going to be this divided by 3, 1 divided by 3, negative 2 divided by 3, 1 divided by 3, all the way to negative 1 divided by 3. Let me factor out the 1/3, and this here is my inverse times the 1/3. You want to divide all of these numbers by 3 to actually get the identity here? Fine. You then pull out the 3. Here is the inverse of this matrix right there. If you multiply the two matrices, if you multiply this matrix by this top left matrix, you should get I3. And you will, I'm sure of that. And if you don't, find your error, either in the multiplication of matrix A with matrix A inverse, or with the work that I did to get what I claim is A inverse. Okay, this completes the section on calculating inverses. We will do some more calculation of inverses in the next section.